Hi everyone. In this video, I want to go into some detail with how we can look for patterns in data from experiments and observations, and how we can compare the claims from a specific model about how some physical system works with a set of data from experiments and observations. These methods are exceedingly useful. They are a central step of scientific inquiry, the ability to find specific patterns in data and use data to test proposed models of physical systems. All of this is essential in pretty much all areas of science. We're going to be regularly applying these methods in the Testing Physics series. So let's see how these methods work and let's jump right in. So suppose we have some experiment or set of observations that relate to measurable quantities that we're going to call x and y. So let's call one of these variables x and one of these variables y. This could be pretty much anything. Say the experiment is me throwing objects horizontally from a certain height and seeing where those objects land. So my throw speed might be x, and how far away they land, that might be the value for y. Or we could do an experiment where I run different electric currents through a wire and measure the magnetic fields around that wire. So x would be how much current am I using, and y would be, well, what is the strength of the resulting magnetic field? Or we could do an experiment where I don't know, bake a cake for different amounts of time and measure, as I change the amount of time that I'm baking for, what does that do to the consistency of the cake? So again, this is a wide range of, we're doing some kind of experiment or making some kind of observations where we are measuring two different quantities. In the experiment, we're going to try to run multiple trials. So if we have our kind of general setup, we might have a first trial, so trial 1, and we get a certain value for x and a certain value for y. If I throw this at a certain speed, where does it land? Then I'm going to do more trials. Say I throw this at a different speed and see where it lands. And we keep on doing more and more trials, and for every trial that we do, we're going to get a pair of observations, one for our quantity x and one for our quantity y. And this is going to be the set of data that we want to try to find a pattern in. How are we going to do this? Well, scatter plots are extremely useful for finding patterns in this kind of data. You may have seen scatter plots before. Let's do a quick introduction on how we would make a scatter plot from some set of data. So when we want to make these scatter plots, we want to put one of our variables on the horizontal axis. We're going to use the x variable for that. And we want to put the other measurement on the vertical axis. We're going to call that the y variable. So let's say I'm doing some experiment. Again, it could be any experiment for what we're calling x and y. They're just two measured quantities that we're looking at. And let's say for our first trial, we had the value of x is equal to 1 and the value of y is equal to 2. If we're making a scatter plot, we want to make this graph and put data points at locations representing the results of each of our individual trials. So for this first one, we'd say, well, I want x to be equal to 1. I want y to be equal to 2, so we are going to put a single data point right there representing that particular trial. What are the values of x and y for that trial? Let's say we had another trial where our value for x was 2.5 and y is 5.5. Well, we can do the same thing. When x is 2.5, y is equal to 5.5, and we can put another data point there. And we basically just repeat this process over and over, looking at all of our different trials. They don't have to be evenly spaced. Some points there might be more data, some points there might be a little bit less data, but we generally want to try to get a wide range of data. So this is how we can identify, how we can graph this data and try to look for particular patterns in how x and y are related to each other. Now, a lot of time we're going to be doing this on computer. There are a lot of different programs that you can use to make these kinds of scatter plots to graph data in these particular kinds of ways. Let's try doing an example using Google Sheets. again, there are lots of programs that we can use for this. Google Sheets is free, it's widely available, so thought we'd use this just as an example. So let's say I want to graph this data. Well, first we have to tell Google Sheets what data we're using. So let's call this variable x. If when you're making these measurements, they're generally going to have units associated with it. So in these label titles, that's where I would recommend saying these are the units that we want to use. If you try to put units in with our actual data values, that's probably going to confuse the program. So in your heading titles, that's where you'd say, I'm measuring in these particular units. So let's say I have some mock data. Let me just kind of randomly throw some values for x in. So just throw a bunch of values in for x. And let's say that, again, during each of these trials, when I was doing my first trial and used 1.1 for x, I measure the value for y, and I got, let's say, 5.6. Second trial, I get a different value for y. Third trial, fourth, fifth, and sixth. So I just kind of like, again, this is mock data. I'm not looking at any particular experiment. We're just trying to find how do we make these scatter plots and how do we graph this data. So once you've got your data on the spreadsheet, the way that we can make a scatter plot out of this is by clicking and dragging to highlight both of those columns. And then you can go Insert Chart. So you go to Insert Chart, and sometimes Google Sheets is clever enough to kind of be able to figure out what kind of chart you're likely to want. In this case, it did identify that we wanted a scatter chart. If it doesn't, when you click on chart type, you can go for a whole bunch of different kinds of charts. But again, in this case, we want a scatter chart. It's also generally going to be a good idea to check to make sure that the chart is actually representing your data properly. So we should have variable x on the horizontal axis. We should have variable y on the vertical axis. And we can check some of our data points. So for example, this data point, when we're at around 2.4 for x, the value of y should be just shy of 11. Okay, that seems to match up fairly well. We seem to have some consistency in how this graph is being generated. Now, if you need to make modifications, you can go to hit these three dots up here and go to Edit Chart. And then if the computer had somehow made a mistake in what it's graphing, notice it has this, this label for what's on the x-axis. Well, we want variable x on that horizontal axis. What do we want for the series, what it kind of calls the vertical axis? We want variable y. If I wanted to switch around which quantity was graphed on which axis, well, we can do that here. We can say, on the x-axis, I want my y variable, and on the vertical axis, I want my x variable. So we can kind of change those around, but let's change it back to the original one so we have our original data. So this is kind of the start of how we can build these scatter plots using graphing programs. Again, in this case, we're using Google Sheets, but there are a lot of other graphing programs that we can use. And once I have this graph, we can try to look for particular patterns in how these two variables relate to each other. How does our quantity x relate to our quantity y? So what are some of the different kinds of mathematical patterns that we might see in some kind of experiment? There are a number of different kinds of common mathematical patterns. These are by no means the only mathematical patterns that exist, but basically these patterns are going to try to find relationships between my variables x and y. So we're finding relationships between our variables x and y. And each one of these patterns will also have what we call fit parameters. So they're going to have these constant fit parameters. These are looking at some of the specific details of exactly what kind of pattern are we looking at, what are some of the parameters of that pattern, what can I change about that pattern. But let's look at an example to kind of iron this out. One of the simplest patterns that we can talk about is the linear pattern, where if you've taken a high school math before, you've probably seen this equation, y equals mx plus b. So for the linear pattern, we have y equals mx plus b, where our fit parameters are m and b. M represents the slope, so this is our slope, and b, we call that the y-intercept. But again, those are ways that we can, those are constant parameters that we can use to identify exactly what type of linear pattern are we looking at. So if we were to graph this, well, that linear pattern, it's just all of my data seems to make a straight line. Okay. If our slope is larger, the slope represents, well, how steep is that line? If we have a positive slope, that line should be going up as you read the graph from left to right. If you have a negative slope, well, that line should be going downwards as you read the graph from left to right. So this is finding, again, a pattern between my variable x and my variable y, and this slope is telling me something about that particular linear fit. Is y increasing as x increases? Is it increasing rapidly as x increases? It's looking for the details of that specific linear fit. These kinds of patterns, these linear patterns, occur when y varies at a constant rate with x. So for example, if I change my value x by, let's say, 1 unit, then my value y should change by a fixed amount. So in this case, since we have this slope of, for this case, 3.36 for the slope, that means whenever I change x by a value of 1, y changes by 3.36. Okay? If the slope was larger, y would be changing more rapidly and we'd have a steeper line. Again, the slope m and the y-intercept b are constant fit parameters, and our graphing programs are generally going to be able to measure this for us. You can measure these by hand, but if we're graphing this in something like Google Sheets, we can get the computer to solve those parameters for us. And in a little bit, we're going to be able to find how these fit parameters can be associated with very specific physical quantities. So we're going to talk about that one a little bit later, but here's our first easiest pattern, the linear graph. For a physical example of when these sorts of linear graphs come, again, it's going to be when y varies at a constant rate with x. So for example, let's say I have an object moving at a constant speed, and I'm making a graph of position versus time. How is my position changing with time? Well, the speed, or technically I should say velocity for this one, but in this case our speed is a measure of how is your position changing with time. So this is how position varies with time. So if this speed is constant, my position is varying with time at a constant rate. So that means I should be getting a straight linear graph out of this, because again, what I've put on my vertical axis, the position, varies at a constant rate when I vary the thing I put on the horizontal axis, in this case the time. Okay. So that's one example. Again, we're going to see lots of examples of this in the testing physics series. Let's look at a second mathematical pattern, the quadratic pattern. Again, if you've taken a high school math course, you've probably seen this before. Y equals ax squared plus bx plus c. You may have done solving the quadratic equation before. But for this particular pattern, the capital A, capital B, and capital C, those are going to be our fit parameters. Again, these are things that we could either measure, or generally we're going to get the computer to measure these particular fit parameters for us. This particular mathematical pattern will give you your nice parabolas. So if capital A is positive, this would be an upward kind of facing parabola. If capital A is negative, well, then it will be a downwards swooping parabola. So again, these fit parameters tell us a little bit more details about the specifics of this parabola that we're working with. Okay. Well, these quadratic fits, will occur when one of the rates of change of y varies linearly with x. So let me give you an example of this. So for quadratic, let's say I have a constant acceleration system. Well, acceleration is how velocity changes with time. But we also said that velocity was how position changes with time. So if I have this kind of a constant acceleration system, then, and I do a graph of, again, position on the vertical axis and time on the horizontal axis, that should give me one of these parabolas. Again, whether the acceleration is positive or negative, that's going to tell us what direction these parabolas are kind of swooping in. But this is saying that the rate of change of position with respect to time, that rate of change is varying linearly with x. So if I have this kind of constant acceleration system, we should get one of these parabolas. In a future testing physics video, we'll be seeing some specific examples of this. Okay? So the position versus time graph for constant acceleration motion, that would give me one of my quadratic equations. We can also get higher order polynomials, so something that has an x cubed term or an x to the fourth term. And those higher order polynomials, sometimes they show up if we're looking at approximations of more complicated mathematical patterns. So we'll see some examples of that later on. I'll again be going into more detail with all of these topics in future videos. But these quadratic patterns show up fairly regularly as well. Another example is the power fit. So let's do a power fit, which has the form y equals ax to the power of b. And again, in this case, a and b are going to be our constant fit parameters. These sorts of patterns occur very, very regularly in nature. This is one of the most common mathematical patterns. Again, you may not have seen this particular form before, but it shows up all the time. This occurs whenever you have a system where changing x by a certain factor will cause y to change by some other factor, and those two factors will stay the same, will kind of keep matching each other independent of the initial values. So for example, let's say I have a situation where if I double x, that means I would quadruple y. That would be matching with this kind of power fit. Or if I have a case where if I double x, maybe this becomes, maybe y increases by a factor of root 2. Okay? That would be another one of these power fit equations. And this should happen regardless of your initial value. So on this diagram, we can say, well, going from 1 to 2, if I double the value of x, the value of y, the vertical part of that, goes up by a factor of 8. Or if I went from 1/2 to 1, so I'm still doubling x by going from 1/2 to 1, then the value of y should still increase by a factor of 8, if this is x cubed that we're looking at. Let's look at some examples of this. So if you consider how the area of a circle relates to the radius, well, if I double the radius of a circle, you can find that the area will go up by a factor of 4. And this equation has this this form that matches our power fit equation. Y, match it up with our area, is equal to some constant, oh, looks like that constant is pi, times, well, our other variable would be the radius of the circle, to some power. Those two equations match up with each other. Doesn't matter what kind of a circle I'm using. If I double the radius, the area will go up by a factor of 4. This is a property that is emblematic of one of these power fits. Another example is how light intensity decreases with distance. So let's say I have a light source and it's giving off some light going in a certain direction. So let's see if I can draw this decently. So that light at this point is fairly concentrated. It's all concentrated into, let's call this 1 unit of area. But as this thing goes further away, if I double the distance, then that light gets spread over 4 times the area. So doubling the distance would cause the intensity of that light to become 1/4 of what we started with. This would be another example of one of those power fits. Changing one quantity by a certain factor will cause the other quantity to change by some other factor. And those factors will keep on matching up with each other no matter what the initial values were. If I double this, what is that going to do to my value of y? What factor is it going to change by? That's going to be a power fit. And for these particular shapes, just to kind of highlight what these are going to look like, if that exponent term, if that b value, if that is greater than 1, well, you're going to get this thing increasing at a greater and greater rate. As x increases, y is going to be increasing at a greater and greater rate. If b is between 0 and 1, then, well, as x increases, y is going to be increasing, but it's going to be increasing at a ever slower rate. And if that exponent is negative, well, then y is going to be decreasing as x increases. So this would be like the light example. If I double the distance, if I go from 1 to 2 or from 1.5 to 3, if I double that distance, my y value is going to become 1/4 of what we started with. Well, this will be the last one for the set that we're looking at, the exponent fit, where y is equal to a times the natural exponent, this e value, to the power of b times x. So this is going to be our exponential fit. So y is equal to a times e to the power of b times x. Again, a and b are our constant fit parameters. If b is positive, well, as we increase the value of x, the value of y is going to be increasing exponentially. If that value of b is negative, then as x increases, our quantity y is going to be decreasing exponentially. And in different kinds of physical systems, this occurs when the rate of change of y, the rate of change of how y changes with x, that's proportional to the value of y itself. So when y increases, the rate that y increases, when y gets larger, the rate that y is going to increase as I make x larger is also going to be increasing. For some specific examples, in population models where we don't have any limiting factors, maybe this would be bacterial growth, where each bacteria is expected to split and reproduce in a certain time period, well, in that case, the birth rate is proportional to the population. The larger the population, the larger the birth rate is going to be, so that will be an exponential increase. Compound interest on a loan. If I have some money invested and there's a certain interest rate of return, the amount of money that I'm getting from that interest rate is proportional to how much money is in there. Radioactive decay. If I have radioactive particles that are going through decays, that decay rate is proportional to how many particles are there. If I have a greater amount of that sample, I'm going to be seeing more and more decays happening. So that would be an an example of an exponential decrease with time. So again, there's lots of different kinds of mathematical patterns that we can identify. And when we're actually graphing these programs, when we're using something like Google Sheets to graph these, we can actually generate different kinds of fits and identify what those fit parameters are. So let's look briefly at how we can actually add best fit curves to this data. So if you have your graph made, you've clicked on your chart and you're going to go to Customize, and then go to Series, and scroll down to the bottom, there will be a checkbox for including a trend line. Okay. So when you hit that, there's going to be some more options that open up. We can identify what type of trend line we want. Looks like in this case, we're going to get a nice linear trend line that seems to match our data the best. And then for the label, we can hit Use Equation. So now what this is telling me up here, let's see if I can make this a little bit larger, a little bit easier to see. We can say that the equation, our linear equation that seems to match up with this form, well, it looks like my slope is 3.58, and my y-intercept for this case is 1.81. We can identify those particular fit parameters. The computer can tell us what those fit parameters are. Again, if we had some other kind of fit, linear is probably going to be the best one for this, but if we have a polynomial fit, well, we could identify this as, don't think I put the quadratic equation on there, but this would be our value for capital A. It's a thing in front of x squared. 3.51, that would be our value for capital B. That's our x value. Let me bring this up so we can kind of see these side by side. So again, our capital A value on this would be this 0.0111 x squared. So the 0.0111, that would be our value for capital A. Our value for B would be 3.51. Our value for C would be 1.91. So we can identify different kinds of mathematical patterns. So for example, if I go to a power fit, this is the one that seems to best get a power fit. This would be my value for capital A, and this 0.824 would be my value for capital B. So we can try out different kinds of fits, identify which one seems to best match our data, and then from those fit parameters, we can extract, well, what are these constant fit parameters? But in these cases, the computer just seems to be spitting out these fit parameters at us. What do those fit parameters actually correspond with? What are actual properties in some of these different cases? So what we want to be able to do is take some claim, some model of how we think the world works, and use these patterns that we're finding in our data to actually test out those particular claims. And again, this is going to be extremely helpful. We're going to be doing this in lots of the testing physics videos, but let's see how we can assign physical significance to what those fit parameters are. Because again, right now the computer is just kind of spitting out these fit parameters at us, but we want to know what do they physically correspond with, and if I have a model of how I think this kind of physical system should work, how do we actually check our data against that model? Okay. So for example, let's say I have this claim that for an object moving at a constant velocity, the final position of that object, the position at some time, is equal to the constant velocity that you're traveling at times time plus whatever your initial position is. Okay, so this is our claim. So let me write this one down. So we've got, and let's say I measure the positions at a bunch of different times. So this would be gathering values for X and Y. And let's say I put time in seconds on the horizontal axis, and I put position on the vertical axis. I apply a best fit, and let's say, again, this is mock data, but let's say I apply a best fit, and I get this particular result. So what we have here, this is our claim, and we want to compare that against our data. So the data that we got, we had an equation for our best fit equation of y equals 3.36 times x plus 7.72. Again, the 3.36 and the 7.72, when we graphed our data and put this into Google Sheets or whatever program you're using, this is the slope and the y-intercept for our 3.36 and our 7.72 that we got for this. So how do we interpret these quantities? Well, let's look at what we put on the vertical axis. We put position on our vertical axis. So we can match up that my final position, that is the thing I put on the vertical axis. Those terms match up with each other. On the horizontal axis, well, that's where we put time. So that value for time, that's what we put on the horizontal axis. Now, to interpret what these fit parameters physically correspond with, we want to take the equation for our claim and the best fit equation for our data and try to keep on lining them up. So if I keep on lining these up, notice that these two terms, my velocity and this 3.36, those match up with each other. So the slope of this position versus time graph will give me what is the velocity of this object. So that 3.36, it is no longer just a number that the computer kind of spit out at us. We can say that that 3.36 value, that should be the velocity of the object. If this claim is actually true, we have a way of calculating what is the velocity of this object. What about the 7.72? Well, if we have that 7.72, we notice that that matches up very, very well with this term for the initial position of the object. So at time equals 0, this object was at a position of 7.72 meters. Again, the computer just spit out what is this fit parameter, but now we can associate it with a physical quantity, and we can use that to check whether our claim actually matches up with our data. So again, if we have these two equations, our claimed equation and our best fit from whatever particular pattern we've found in our data, we can line those up and give a physical interpretation of what those fit parameters, in this case the slope and the y-intercept, actually correspond with. This is a method that, again, is super, super useful. I was actually never formally taught this. I don't remember ever being taught this in a classroom. I just remember doing labs where the lab instructions would say, make this kind of a graph, put this on the vertical axis, put this on the horizontal axis, and then when you take the slope will be equal to this other weird thing. And my response was, how in the heck did you determine that? Where did that slope thing come into play? How did you know that for this weird kind of graph, that slope would correspond with that physical quantity? This is a very good way on making that identification. Let's try another example. Let's say we're looking at Newtonian gravity. So in Newton's theory of gravity, the force of gravity should be equal to this constant capital G times the values of the two masses that are interacting. So this is looking at a case where I have two masses, M1 and M2, that are a certain distance apart from each other. And we want to know how strong is their gravitational attraction. If we have this force of gravity that's pulling on the two objects, how strong is that force of gravity? And again, the claim is, the equation that Isaac Newton came up with is the strength of this force of gravity should be this capital G, this constant value, times the two masses divided by the separation distance between those masses squared. So this is our claim, that our force of gravity is equal to capital G times m1 times m2 over r squared. We can write this in a slightly different way that's going to allow us to predict what type of fit might be most effective. So I can write this as the force of gravity is equal to G times m1 times m2 times r to the power of negative 2. Instead of writing 1 over r squared, I can equivalently say this is r to the power of negative 2. If we go back through our different types of patterns, we want to identify which pattern, if I have an experiment where I'm changing the separation distance, I'm changing this value of r, and I'm changing our force of gravity, which pattern might be the best match? Well, the linear pattern, it doesn't have any exponent up here, so that's probably not it. For a quadratic, well, we've got x to the power of 2. This is going to be to the negative 2, so that's not going to be our pattern. What about this one? Well, one of the things we're measuring is going to be this gravitational force. The thing that we're changing is this distance, and we're taking that value to a certain power. We want to test out whether or not that this power is actually negative 2. And we're also going to want to figure out, well, what's this multiplied thing in front of it? So this is going to match, again, according to the claim, this should match up with a power fit. Again, exponential, there would have to be a natural exponent there. We don't have that, so it's probably not going to be the exponential. So if we go back to this one, let's say I gather some data where I keep the masses the same, but I change the distance between those masses and I measure what is the gravitational force, the strength of that force, as I move those to different positions. Well, we can graph that data. And again, this is mock data. I have not actually done this experiment. You'd need very, very large values of mass to get significant forces. I have not done this. This is mock data, so just being straightforward with that. And let's say I get this particular pattern. I measure this, and when we look at our data, we have y is equal to, in this case, we got 2.75 times x to the power of negative 2.02. And we want to evaluate whether or not our data supports our claim. Well, how do we match up these terms? Well, let's look at what we put on the vertical axis. On the vertical axis, I put the force. So on that vertical axis, we've got our force. On the horizontal axis, we have our separation distance. So those match up with each other. So if we did this experiment perfectly, which again, there's no such thing as a perfect measurement. There's always going to be some amount of measurement noise in here. But if I were to be able to do this experiment perfectly, then this exponent should have matched up with negative 2. Is it going to match up perfectly? Probably not, because again, there is always going to be some level of measurement error. But we can see that we got something very close. We would have gotten, again in this mock data, we would have gotten something very close to the expected value. If I did this, took these measurements, and I got something like x to the power of negative 4, or x to the power of negative 0.3, or x to the power of 7 or something completely different than negative 2, that data would not support the claim. But if they match up fairly well, then we would say, okay, this data does support this claim within a reasonable experimental accuracy. If we went a step further, well, what should this 2.75 match up with? Well, in this case, it would match up with this combination of Newton's gravitational constant, this capital G value, multiplied by what were the two masses that we were using in this equation. And again, if you knew the value of G, or the proposed value for G, and you knew the two values of the masses, you could actually check this. You could check to see whether your data supports the claim or whether it refutes the claim. Do those match up to a reasonable experimental accuracy? So again, this is something that is exceedingly useful for being able to compare some set of data and test that against some claim. Couple last points that I want to use. When we're using these fit equations and these fit parameters that the computer spits out at us, one of the advantages is that these fits that we're using, they use the entire set of data. We're not looking one data point at a time, because if I just have one individual data point, it's really hard to determine how much noise there is. Is this consistent with the rest of the data that I've taken? By applying these best fits, we find the pattern in the entire set of data. And we can find whether that pattern of experimental data matches up with the claim or not. This is extremely helpful in identifying how much noise might be present in your system, the kinds of noise that show up. We'll talk about this in future videos. The kinds of noise that show up, that's going to be different from case to case. And again, we can use these patterns, we can match up our claim to our data to actually assign physical significance to these fit parameters. Again, allowing us to calculate and evaluate new things and provide new tests of these claims. One more thing that I want to mention is when we're doing our experiments and taking this data, we generally want to look over as large of a range of data as possible. Because sometimes if I'm only looking at a small section of data, we might misinterpret what patterns are actually there. So for example, let's say I took some data and I graphed my x variable and my y variable, and I got something that looks like this. What kind of mathematical pattern are we seeing? Well, pretty quickly we'd say that looks like a linear pattern. But if I zoom out and I start taking more data, maybe that data was just this little part here. It looked like it was a linear pattern, but now we've got these changes over larger ranges. So we might look at this data and say, hey, that looks like a parabola. So I guess this is going to be a quadratic fit. Well, let's say we zoomed out and looked at even more of the data. Now we've got this oscillating pattern. This would be a sine fit for this. Again, there are other kinds of patterns that we have not talked about yet. But this is just kind of a warning that when you're taking data and when you're graphing that data, you should try to graph as large of a range as you are able to get given your experimental setup. Again, depending on your experimental setup, there might be limitations for how wide of a range I can take. For example, if I'm throwing objects and seeing how far they move before they hit the ground, there might be a limitation to how hard I can throw the object. So I might not be able to get an unlimited set of data. But when we're doing these measurements, we want to try to get as large of a range of data as possible. So in the testing physics series, we're going to be seeing these methods applied all the time. They are extremely, extremely useful methods in being able to specifically test the claims that are made by some model that someone may have proposed. So we'll call this good for now, but in future videos, we're also going to be going into more details of how I can look at more of the details, look at different ways of graphing data, different combinations of graphing data, to try to find more of these specific mathematical patterns. So we can go into more detail with saying, I have a particular claim and I have a set of data. How do I identify whether that set of data supports our claim or refutes that claim? Which again is what science is all about, making testable models of nature and then trying to actually put those models to the test using data. So that's it for this video. As always, thank you for your kind attention, and I'll see you in the next one.